Good afternoon. This is the 3.9 video about variation of parameters, and that's officially what this video is about, but I thought I would give you some context for what variation of parameters is. So in this book, we have two methods for finding the particular solution. That's our YP. That's half of our general solution. The first method was something we saw in the last video, which was undetermined coefficients. So those undetermined coefficients were the capital A and capital B and capital C that we were solving for last time. And that was all based on G of t. So the benefits of this method of undetermined coefficients is that really all this is lots of algebra. Right, we never had to do any calculus to solve for that, so you can find a general solution just using algebra. The other benefit of this, or not really a benefit, just comment on it, is that it's only going to work when our G of t, so that's the right-hand side of your non-homogeneous differential equation, it's good for when G of t has the form that involves one of these three things. So when it's either got some kind of exponential term, when it's got either a sine, and I'm just going to put a 2 out in front here, just to say we can put some numbers out in front here, or if it's some kind of polynomial. Right. So if it's some combination of those three things, then we can use the method of undetermined coefficients. The variation of parameters, I'm just going to go ahead and spoil what this is right now, and then I'll talk about what the different parts mean. But the variation of parameters, we end up just having one big formula that we can use to find the particular solution. So y of p is going to be equal to negative y1 of t multiplied by the integral of y2, and I'm going to put some z's in here instead of t's. I'll talk about y in a second. And that's all divided by this w of z. So this is the Wronskian that we saw earlier. So that was our check to see that we have fundamental sets. So it's this integral plus a similar integral, which is going to be y2 of t times the integral of y1 this time times our g divided by that same Wronskian. And that completes the equation for this. So particular solution is equal to the two of these. And one more thing that I need to do here is to add some t's up top here. A quick explanation for why we kind of use this weird notation to talk about z's here. You can think about these as being like t values, but you might have seen in Calculus 2 or maybe at the end of Calculus 1, we talked about integrating some function, let's say x squared dx or something like that. And the result of that, if we have the integral of x squared and it's an indefinite integral, this is going to be 1/3 x third, and then you had to add some plus c on here. So there's going to be some situations where we want to have a plus c in there, and we're going to have some situations where we don't want this plus c. In this case, when we're finding our particular solution, if we had a plus c here, I want you to think about what would happen with that constant. You'd have this equation, your sort of antiderivative, and then you'd have a plus c on here, and that plus c would end up just getting multiplied by y1. So you'd sort of end up with a c1, y1 type situation. The constant from this one would end up being c2, y2. And when I write it like this, you can probably recognize that this is part of the complementary solution. And if it's part of the particular solution already, then we're kind of doubling up on our C1 Y1s and our C2 Y2s. So we want to avoid that by not including the C. So the way that we do that, rather than just say don't include C on here, the Calculus 1 method for this is to not talk about x squared, but talk about t squared, and then integrate it from x to 0. All right. So what that'll produce is just 1/3 t to the third. We evaluate it from x to 0. So this just gives us 1/3 x to the third without any plus c in there. So essentially that's what we're trying to do here. We're trying to just make sure that we don't have a plus c there. When I start to think about this equation, or when I'm memorizing it and trying to recite it from memory, I think that a lot of these inputs are a little bit unnecessary, so I'll write the sort of shortened version that I think might be helpful. So keeping all that in mind, we can say this is negative y1 times integral of the other one, y2 g over w. And I'm just going to call this dt. So this is a little bit sloppy, but I just kind of want to make the point that this is not an insanely long equation like it looks up top. So the y1 and y2 in this equation are going to be from your particular solution. All right, so you found y1 and a y2 in your, sorry, I keep calling that the particular solution, the complementary solution. And the Wronskian is going to be equal to the determinant of y1, y2, y1 prime, y2 prime. And G is your G of t, which is the right-hand side of the non-homogeneous. Differential equation. So that's all the pieces, and you might, after coming out of the method of undetermined coefficients, so what we did in the last section, 3.8, you might get the impression that why would you use anything other than this, right? So that other process was really, really long, and it seems like you could just solve everything with this particular solution. And I will say that's true. So I'm going to write this method works what we'll call all the time. But the one big assumption that you have to make here is that we are assuming that you can integrate it. If you can't solve the integral, right, if it's not one of those very nice U substitutions or integration by parts, you'll need to know how to do the method of undetermined coefficients. So a really common question that I'll get when it comes to finding the particular solution is, do I need to use this method or can I use the other method that's my favorite? And I think the safest answer for that is you should know how to do both methods. And in addition to knowing how to do both methods, you should also know how to distinguish when it's a good idea to use one differential equation, or sorry, one method for finding the particular solution over another one. So the big deciding factor here for this one, in my mind, is for the 3.8 method, if your g of t looks like this, all right, it's either got an exponential, a sine or cosine in it, or if it has some kind of polynomial, like I wrote up top. If your g of t is any combination of this, these three things, then I would use method of undetermined coefficients. If it's anything else, then you should use this method. Depending on who your instructor is, they might ask you to solve a differential equation using a particular method and kind of force you to use that method. So I am not going to do that. If I tell you which method to use, it'll be a hint, but yeah, this is kind of your big deciding factor. Does it have one of these forms in g of t, or for example, if you have something like g of t is equal to natural log of t, you're going to have to use this method. Another comment that I'll make on here is that in order to make sure that y1 and y2 and g and the Wronskian all come together in both cases to form some kind of integral that you're able to do easily on paper, really everything has to sort of fit into place. This is not going to work on some random, if you just choose some random equations that need to work, this can become really complicated really quickly. So yeah, I'll just kind of have that bit of warning there. But when it does work out, this works out really easily, right? The problems in your book are designed to, demonstrate the beauty of variation of parameters. Okay, speaking about the beauty of variation of parameters, I've got two methods. Well, maybe I don't want to say it that way. Let's just work with this example and I'll kind of talk you through that. One of the things I'm learning about teaching online is anytime I don't know what I'm going to say next, I will ask anybody if they have any questions, and that'll give me a second to think. But there's no point in doing that, so I have to just keep talking the whole time. A little bit of an adjustment for me. Okay, so right away we can see that this is one we're going to have to use the 3.9 variation of parameters method, and I'm going to ask you to find the general solution. First thing we need to do is to find our complementary solution. So that involves the corresponding homogeneous case we're going to assume that y is equal to e to the lambda t, and that's going to give us lambda squared minus 2 lambda plus 1 is equal to 0. And this is a repeated solution, so we get that lambda 1 and 2 is going to be equal to negative 1. See, I tried to skip a step and I ended up making a mistake that happens all too often. All right, so this is our actual expansion of this, and so this tells us that lambda 1 and 2 are both equal to positive 1. So this means that our y1 is going to be equal to e to the t. y2 is going to be equal to t e to the t, and our complementary solution looks like this. So that's it for the complementary solution. Our particular solution is going to look like this. So I'll go ahead and write the formula, or I'll write the abridged version of that formula. I think I wrote a T there. So just, again, keep in mind we're cheating a little bit by using this y2 and g and w here. These should all be in terms of z and then taking the antiderivative, but as long as we keep in mind that we don't add a plus c here, we're going to be just fine. So let's start off with finding our Wronskian, since we already have y1 and y2 listed up here. So our Wronskian is going to be the determinant of y1, y2, y1 prime, and this one, I'll just ask you to trust me on this one, but you need to do a product rule for this, but you end up with t plus 1 times e to the t. What this equates to when we take the determinant is we've got t plus 1 times this piece here, which is e to the t times e to the t, so that's e to the, think about that, if that's t squared or 2t. All right, convince yourself that that's 2t. And this is minus t times 2t. So we have t times e to the 2t minus t times e to the 2t. Those two cancel out, plus 1 times e to the 2t. So we have e to the 2t. Turns out that this is not 0, right? This exponential function can never be 0, so we know it's a fundamental set. But really all we're trying to do here is just say e to the 2t, that's our Wronskian. Right? So just along the way we proved that it was a fundamental set, which is good. Okay, so I'm just going to go ahead and plug everything in here and start solving these integrals. I guess we can remind ourselves that g of t is from our original differential equation. So that's going to be natural log of t times e to the t. And hopefully these will turn into some nice differential equations or integrals for us to solve. Okay, so we've got negative e to the t times the integral of y2, which is t e to the t, times g, which is ln of t e to the t, divided by e to the 2t. That's nice. And this one is t e to the t, integral of e to the t, ln of t e to the t, e to the 2t. And we get something pretty nice for both of these. Assuming you know how to do it, right? Important crossroads here. Do you know how to do these integrals, right? Is this a U substitution? In this case, neither of them is a U substitution, right? There's no point in trying to call this one U. It's just not going to work, right? We would just be renaming t. And so in the absence of knowing how to do this any other way, we need to try integration by parts. So I'm going to kind of split this up